Greetings, I am Sipahioglu, and today I'll be talking about a simulation-based approach to understanding urban growth scenarios. I am currently a Master of Science student of Architectural Design Computing program at Istanbul Technical University. I am also a research assistant at Yaşar University, Department of Architecture. This study is based on my master thesis, which I'll be defending next month. I have my degree in architecture, and I am specializing in computing branch of architecture. But what makes me so interested in urban features? And how can I use my skills in architectural computing in understanding those features? This study is the accumulation of my interest in urban growth and need to understand the complex relationships it embodies. I will briefly explain the arguments regarding the complexity of the city, then how urban simulation models are developed in regards to complexity. After that, I'll be moving on to my study and its structure. I will conclude my presentation with the findings of the simulation and its implications in the context of urban simulations. Cities are changing, growing, and at times shrinking under the effect of complex relationships which we are mostly unaware of. Jane Jacobs says that overplanning and segregating influence areas like districts and neighborhoods for the sake of creating perfect shapes are the root causes of the simplification of complex urban structure, which brings about cities that are difficult and ill to live in. Christopher Alexander argues that each element in the city creates its own influence area, and it's in other elements' influence area. Accumulation of these areas construct the complex structure of the city. Since the overplanned or ill-structured cities are simple, they are unable to grow successfully and function effectively. It is accepted that cities are complex systems, and mathematical computing helps producing more realistic results in understanding cities where human mind is inefficient. According to Lefebvre, the city is a comprehensive phenomenon that cannot be tied to a single discipline. Beyond being tied to one discipline, the city doesn't belong to any science, no science denies the city and cannot fully study it. He says that a formation that brings together all the sciences from mathematics to sociology in order to understand the city may be sufficient. But he also states that it is not possible to make a full analysis of the city with such formation. The city is argued to be not just an object to sociology, but a chaos and disorder that conceal a hidden order. From there, he questions the scope of urbanism and its implications regarding its position in architecture and urban planning. If we think we know what urban is, we don't need a science, he says. But if we don't think we know it, we are right to search for answers to this question. Is it global? Is it a means to a technology? Is it a false claim or an ideology? Let's look at the shift in the perception of urbanism and complex science. With innovations in informatics and the transformation in scientific thinking, the idea of the city has changed. Monocentric conception evolved to an understanding where city centers were disintegrating and sprawling. It can be argued that the breaking point in this change was the Turing machine, which is the foundation of the modern computer. General systems theory and complex systems theory gained value with the Turing machine, and they changed the way we thought about cities. Cities then could be treated as systems, not as monocenters with everything placed around them. Computers became powerhouses for calculating cities as systems. As these new thoughts and calculation systems matured, the understanding of the city as a computable system evolved again. Cities are now regarded as complex systems which display behaviors that are impossible to concretize as strict structures. There is randomness and uncertainty. On one hand, humans tend to make sense of complex systems by oversimplification. On the other hand, human decision-making process is treated as complex. This dichotomy of the tendency to oversimplify cities and the complexity of decision-making in urban planning necessitate an urban growth model as a decision support system. At this point, simulation models come forward. My study finds itself in the intersection of complex science, geographic information systems, and urban growth. I use urban simulation as a tool for investigating urban growth scenarios. The interest in urban simulations increased with the need for understanding complexity of the cities and accelerating urban growth. As the theoretical foundations of simulation models were laid, and hypothetical calculations on hypothetical cities gave satisfactory results, real simulations started to be applied on real places, with geographical information systems becoming widespread. In the 2000s, the diversity of models increased with sample studies gaining speed in their advancement. There are more than tens, maybe hundreds of urban simulation models, and not one is the same as the other one. This fact itself verifies the complexity and difficulty in urban simulation studies. It also proves the fallacy of standardization and oversimplification of urban theories and models. Simulation models don't aim to explain causes of urban growth. The interpretation depends on the modeler, the datasets, and variables they use. Simulation results are not absolute. They reveal future possibilities humans tend to overlook. Since simulations are almost always case-based, they require the modeler to think the data and the setting they will use thoroughly. This extensive process enhances the understanding of urban growth factors. Some of the major and recent simulation models are listed in the table. This is a very limited table of the models available today. We can deduct from this limited table that the models vary greatly in the combination of methods they incorporate. In this study, I used a recent model called FLUS, Future Land Use Simulation Model, developed by Liu, Liang, and their colleagues. This model utilizes cellular automata and artificial neural networks in predicting future scenarios. The simulation is based on the data prepared through GIS software. In this study, the land use data and the driving factors of urban growth scenarios were prepared in QGIS. As it can be seen from the flowchart, simulation process requires the occurrence probability to be computed first. Then, this probability data is used as a basis for cellular automata and competition mechanism simulation. Cellular automata settings are adjusted heuristically. When people think about Turkey, the first thing comes to their mind is Istanbul. After that, it is Ankara, the capital city. Izmir, despite being the third largest city with a population of 4.3 million, seems to be forgotten. The change map showing the urban growth between 1990 and 2019 indicates a greater growth in the future. This is a city that needs to be regarded more in local and global sense. For this reason, Izmir was chosen as the case study. Izmir's development plans and strategies were analyzed. Simulation scenarios were based on these plans. What are the features planned for this city? How the development decisions will affect its growth? What are the factors of urban growth? How can we visualize its features with urban simulations? How the factors of urban growth influence the results? I am trying to find answers to these questions. Simulation scenarios were based on development points and corridors determined by Izmir Development Agency in the regional report they published in 2015. The report puts an emphasis on agricultural and industrial development. It draws the importance to tourism. There are also points of regional development. 6 different scenarios were established according to these development plans. The map shows the towns and their relations to the industry-specific plans. We will be looking at the results of the points with dashed circles more closely. These points are either the merging point of 3 different sectors or show different behavior than the rest of the city. This table shows the scenarios and their driving factors. Baseline scenario is a must in every scenario-based simulation to compare the results. This is the most basic scenario, only incorporating the minimum. Transportation scenario has more data regarding the routes, but the results indicate no distinct difference between this one and the baseline scenario. Agriculture, industrial, tourism, and regional scenarios are characterized with the driving factors in columns 5, 6, and 7. Development points are based on the points shown in the previous map. For agriculture, it is important that development regards existing greenhouses, rivers, and streams. Industrial development will be affected by the existing and planned organized industrial zones and power plants. Izmir intends to remain a harbor city, so harbors are of great significance for regional and tourism scenarios. Tourism scenario also incorporates tourism attraction points. First rule of geography according to Tobler is this: everything is related to everything else, but near things are more related than distant things. In the light of this law, the Euclidean distances of driving factors are computed to be used in simulation. This is Torbalı. Torbalı is a point where agriculture, industrial, and regional focus merge. Agriculture scenario suggests growth towards south to the greenhouses. Industrial scenario growth, however, is towards north to the industrial zones. Regional scenario shows an equal amount of growth around the built area. Bergama is the other point where three different sectors come together. Here these sectors are agriculture, industry, and tourism. Agriculture and tourism suggest similar growth patterns. In industry scenario, there is a region that shows no development. Comparing the result with driving factors doesn't help identifying the reason behind this. This is a possible example of stochasticity of the model mimicking the real urban growth. Urla is a point which is more different than the previous points. Here the focus is on tourism and regional development. Most prominent growth is seen in regional scenario. As a tourism point, it also grows substantially. The least development is seen under industrial scenario. As the town is far away from most of the industrial focus points and driving factors, this is expected. When we look at the big picture, we see that the regional scenario doesn't offer any development towards the administrative boundary of the city. The reason for this is that the harbors are along the coastline and regional development points are central to the city. Combining this scenario with others is a possibility for future work. Baseline and transportation scenarios don't differ much in growth they demonstrate. The difference is that, as expected, there is more aggregation around new roads under transportation scenario. Simulating these scenarios is effective in seeing what happens when there is no substantial driving factor of urban growth. Results are much more informative under agriculture, industrial, and tourism scenarios. Driving factors differ prominently, and this produces different areas of incremental growth subjective to the scenario. It is difficult to establish a general framework of urban growth due to its complexity and the variability of urban definition. The question of what urban area is changes in every study. Therefore, analysis and simulation characteristics of each study vary. Simulation settings, land use data, driving factors, methods employed are customized for each individual case. The studies are often interdisciplinary, since urban growth models require knowledge from a variety of fields. Application of these models calls for a deeper understanding in both urban theories and simulations. Comparing all the results in detail shows that working with several scenarios produces many possibilities for each area within the city. It underlines the importance of planning policies and decisions. Correct selection of relevant driving factors imitates real urban growth directions. It will be interesting to see the implications of different combinations of these scenarios and the driving factors in the future studies. Another direction is to incorporate regional dynamics with neighboring cities in the case of Izmir. The selected model is consistent in producing acceptable results. Its use of artificial neural networks in calculating probability of occurrence data makes it efficient in handling nonlinear spatial data, which at times can be non-essential to the case. The simulation models are more than capable of being used as decision support tools, and the interest in the research area just shows that. The quantity of the studies, the validated urban growth models based on complex science, emphasize the importance of including them in real planning applications. Combined use of planning policies and urban simulations will help improve the models and decision-making processes. The drawback is that the urban simulation process is long, and it requires expert knowledge. Reaching a result might take much longer than the policymakers would want, or the allure of the simulations might take away from the importance of taking actions. In short, they need to be handled with care and awareness of the theoretical and technical background they call for. It must be kept in mind that there is no certainty in the results, but many possibilities. Thank you.